Hello everyone, welcome to this video. In this video, we're going to look at how to graph rational functions using GeoGebra, which is a dynamic mathematical software designed to enhance the teaching and learning of mathematics. GeoGebra can be downloaded from the internet. It enhances conceptual understanding and then students' engagement when rightfully used. Before we go into the actual plotting, let's first have a brief overview of rational functions. A rational function is just a ratio of polynomials, and it's given by this general expression here. F of x is equal to e of x over q of x. In a rational function, the denominator, which is q of x, should never be equal to 0. In mathematics, when the denominator is equal to 0, it forces us to divide by 0. And division by 0 in mathematics is impossible. Practically, we cannot divide by 0. So when we're dividing by 0, it forces the function to be undefined. We say the function is undefined, or in a more complex mathematical term, it's infinity. So in a rational function, q of x must never be equal to 0. When the q of x is equal to 0, the function becomes undefined. Let's look at some key features of rational functions. One, we have the domain should exclude zeros of x. So that means at any point where q of x is equal to 0, the function is not defined, so it's not part of the domain. We have the asymptotes. The asymptotes are just lines in the graph related to the function where the function is not defined. Asymptote can be a line, so you will see that the curve will not touch the line called the asymptote. So at the asymptotes, this f of x is not defined. One, we have the vertical asymptote, which is got by solving the denominator here, q of x. You just equate it to 0 and solve. There you'll get the vertical asymptote. Then we have the horizontal asymptote. This is how we get the horizontal asymptote. When the degree of p is less than the degree of q, the horizontal asymptote, which is normally represented using y, is equal to 0. The degree is just the highest power of the polynomial. Okay. For example, here when we say the degree of p, we mean the degree of p of x. For example, when you have a polynomial like a quadratic equation or a quadratic function, that is a polynomial. In a quadratic equation or function, the highest power is 2. So that highest power of 2 becomes the degree. When you have a cubic function, the highest power is 3. So that becomes the degree. So the degree of a cubic function is 3. When the highest power is 4, the degree is 4. When the degree of the numerator is less than the degree of the denominator, the horizontal asymptote rather is y equal to 0. Then when the degrees are equal, then the horizontal asymptote represented by y is given by the ratio of the leading coefficient. So let's take an example here. Here we have a simple example. A rational function f of x equal to 2x over x minus 1. So you can get the domain here. Earlier when we said the domain of the rational function is all values of x except the zeros of x, the zeros of q of x rather. So here the domain of this is all real x except where the denominator is equal to 0, because when we equate this to 0, we get x equal to 1. And when you put 1 here, the denominator becomes 0. That leads us to divide by 0. It makes the function undefined. Then we go to the vertical asymptote. So when we want to get the vertical asymptote, we just set the denominator to 0. When we set this x minus 1 to 0, we get x equal to 1. So at this point, x equal to 1, our function f of x is undefined. Then the horizontal asymptote here. So here you see that the degree numerator is equal to the degree of denominator. This is p of x, this is q of x. So when we want to get the horizontal asymptote, is the ratio of the leading coefficient of numerator to ratio of leading coefficient of numerator, which is 2 over 1. So our horizontal asymptote is y equal to 2. So at this point, y equal to 2, or this line y equal to 2, the curve of f of x should not touch. It just gets near, but it shouldn't touch. You're going to see in GeoGebra when we are plotting. Then we have the intercepts. For you to be able to plot any function, you need to know the intercepts. And we have the x-intercept. This is the point where this function cuts, or the line of the function cuts the x-axis. And at that point, the value of f of x is 0, or y is equal to 0. So you just equate this to 0, and you get the value of x to be equal to 0. So that means this function f of x cut the x-axis at 0. That's why you have uh, 0, 0 here. Then you also get the y-intercept. At y-intercept, the value of x is 0. So that means you get f of 0. Getting f of 0, substitute 0 here, you see you still have 0. And the coordinate is 0, 0. So when you have the asymptotes and then the intercepts, you're good to go. You can plot the graph. That's when you're plotting by hand. But in GeoGebra, we are just going to take in a little bit different procedure that you're going to see. All right, let's now open GeoGebra and see how to graph the function, the rational function that we just saw earlier. So when you want to plot this function, you come to this area here. This is the GeoGebra interface. You have this plus, this area written on input. You just insert input, and then you enter the function. So the function is f of x equal to 2x. You see, GeoGebra plots immediately. The moment you put in a function, it plots. For example, here it has plotted f of x equal to x. That is the graph. But we are not interested in that. For us, we're interested in 2x divided by x minus 1. So you put in the forward slash for the division sign, and then you type in x minus 1. So literally, this is the graph of the rational function f of x equal to 2x over x minus 1. So when you look at this graph, you see the way the curve is changing or moving. You see, this is the line y equal to 2. You see the curve is not touching here. So when we try to pan the interface at the grid, this one has been set to infinite number of points. You see, the curve is moving. This is up to around x equal to negative 24. This is the line y equal to 2. It's not touching on this line here. So the asymptote is just that line where the function should not touch. The function is undefined at that point. See? Rational functions always have so many branches that are determined or influenced by the asymptotes. You see there's another branch here. You'll see this is not touched. It's not touching x, I mean y equal to 2. That is the horizontal asymptote, which you saw how we got earlier, the interface of our nodes. And then we have the horizontal asymptote, the vertical asymptote rather, which was got to be x equal to 1. You see, this is the line x equal to 1. You see? So this curve is not touching the line. The curve is not touching at all. Even if you extend the values, so here the x values have been extended to, let's try to go down and down and see, this is now negative 43, just close to the line. It's not touching. It doesn't touch or cut, because at that line x equal to 1, the function is undefined, so it doesn't cut. When it cuts, then we don't have a function, because that point is division by 0. That point is division by 0. You even see on this other branch, when it comes close to x equal to 1, it's like the curve is repelled. You get, the curve is repelled. So let's include these asymptotes on the graph and we see them. Since we've already discovered that the vertical asymptote is x equal to 1, we just come here and plot x equal to 1. See, the line is drawn there, x equal to 1. So we can remove that label there and remove that label. Move that label from settings. So you see this? That is the vertical asymptote. Let's also put the horizontal asymptote, which is y equal to, see it's there. So normally when graphing rational functions, the asymptotes are represented by dotted lines. So what we can do is click on these lines here, right click, and then click here. You see we have dotted lines, so we can put here dotted and even change the color. We can change the color to, let's say, gray, something quite visible. We can even use black. Do the same here because the asymptote is not part of the curve of the function. So what we need to do is make it some sort of discontinuous line so that it is distinct. So this is how you graph rational functions. By hand, you would also do the same thing, but here we have used GeoGebra, and we can add a label. We can add a label from tools here. Add a label from tools, text ABC, so that whoever comes and check on this knows that we have graphed. We have graphed f of x, f of x equal to f of x equal to 2x over 2x over x over, you can also bring in latex. This is 2x over x minus 1. Remove this b, then you click OK. You see it's there. It's there. You can cancel. Then come back to the move tool. You can move it around. Thank you for watching. If you found this video useful and you learned something about graphing rational functions, please hit the subscription button or subscribe and then turn on all notifications so that next time I post a video about any other concept in mathematics, you are able to see the notification on your phone right away.